Welcome to my first proof. This is one of my favorite proofs, and I used to show it to a class of students who were not math majors, and it was something they felt they could follow, and they thought actually this wasn't real math, which is really interesting because this is real math. So I'm going to prove for you that there are an infinite number of primes, and the first step is you have got to believe it. That's why we did something in class where you just kind of thought about it a little bit. You should never do a proof just because the teacher said so. Your first step is to actually spend some time messing around with it to see if you believe it. Because if you don't believe it, it's going to be all the more difficult to prove something. And this is one of those steps where I'm going to tell you that this is the way to do it, and you all are going to ignore me. And then one day you're like, oh, I remember she said something like that. Because initially the gut reaction is just to go by the book and do it because the teacher said so, or something in the book said it was a problem. But sooner or later you're going to come across something that isn't true that you're trying to prove, and that's when it's going to sink in. We're going to use something called proof by contradiction, which is in chapter 5, but like I said in class, we're going to be spacing materials, so that's just the way you do this proof. That's the standard way to do this proof, and that's because in this case there's a black and white condition. There either is an infinite number of primes or there isn't an infinite number of primes. There's no in between the two. And so this sets it up perfectly. Moreover, if I try to prove that there's an infinite number of primes directly, I'm going to have a hard time doing so because proving something has an infinite number of primes, I mean, where do you go with that? Well, I could start with 2, 3, 5, 7, but then 11's prime and 13's prime, so I can't actually put my finger on each prime. I have nothing to get my hands on or sink my teeth into to work with. So it just seems like just proving it directly would be nearly impossible. There might be some way, but usually the way I think is there's got to be an easier way. So I really have nothing to work with. So what I'm going to do is assume the opposite, that there's a finite number of primes, and the way a proof by contradiction works is, since I really don't believe the opposite is true, I believe the first part's true, I'm hopefully going to arrive at some conundrum. And you're going to see me arrive at the conundrum, and you'll know what I mean by conundrum. So assume, on the contrary, there's a finite number of primes. In your syllabus, in your course description, they say that part of this is about writing. Important to let your reader know that's what you're doing. Always lead your reader. And good writing, I'm actually a minimalist when it comes to writing. Good writing is try to make your reader not grumpy. I've reviewed papers where they don't lead me on and let me know what they're trying to do. There's nothing wrong. There's no set way to write a proof. Just make it easy on the reader's eyes. All right, so I let the reader know that I'm going to assume the contrary. There's a finite number of primes. What does that mean? Well, that means that I can actually list them out. P1's the first one, P2's the second one, P3's the third one, and the dot 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 would keep going unless I stop it at some point. I mean, there's a finite number, it means there's a last one that I can actually list out. If there's an infinite number, the dot 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 would just keep going. Notice here I put that prime numbers are bigger than 1. By definition, a prime number cannot be 1. Or minus 1. So some definitions say that prime numbers are any integer that's divisible only by 1 in itself. Some force you to have them only as non-negative integers that are bigger than 1. Either way, it cannot be 1. Now comes a trick. I've seen it before. Sometimes proofs are tricks. And what you do is you squirrel those tricks away, and when you get an unknown proof, you apply that same trick, or think, oh, that reminds me of that proof that I had that was like this. So you're starting to acquire a box of proofs to pull from in case you have something similar. So I'm going to let n be the product of all these primes. Now the primes might be in the thousands and the millions, so this could be a beast of a number, but I'm certainly allowed to make a product out of them, so I'm going to make a product out of them. My game plan, why I did this, is to come up with two numbers that can't possibly have a common factor, but end up doing so, and I'm going to utilize my primes to get that common factor. So when I make this product here, what I've done is every single prime is a factor of this number n. Here's my second number. If I take n plus 1, it's going to be that beast I just made plus 1 added to it. I'm just going to pop that number out of a hat and put it there. Why is this number important? Well, n plus 1 is an integer. And when you're little, you made these prime factorization trees, and you know that I can break up any integer into a prime factorization tree with primes that divide it. So there's got to be at least one prime that divides this n plus 1. My students from the class where they weren't math majors said, hey, it's that tree thingy that we did. Tree thingy is a word. The big people word is called fundamental theorem of algebra. So there's a theorem called fundamental theorem of algebra that says that every non-negative integer can be factored into primes. Well, you're allowed to do this unless inside the theorem itself, the fundamental theorem of arithmetic, they use the fact that there's an infinite number of primes. If it used that fact, my logic would be circular. But we are good here. It doesn't use the fact that there's an infinite number of primes. So I'm allowed to use this because it doesn't depend on there being an infinite number of primes. My PI must also divide n. Why? Class, hopefully someone will answer and say, well, that PI must divide n because I made n that way. I made it as a product of primes. So PI divides n, and PI divides n plus 1. In fact, you can prove that two consecutive integers cannot have a common factor other than 1. But let's take this further. That for something to divide something else, it means that I can express n as PI times some stuff, and n plus 1 can be PI times some other stuff, maybe, if PI is a factor of both of them. Well, I don't use word stuff and other stuff. I'm not George Carlin. So I'm going to replace stuff with D and replace other stuff with T, with the initials of my name. Now watch this. 1 is n plus 1 minus n. That's true. I'm going to replace n plus 1 with pi times t, and I'm going to replace n with pi times d. Then I'm going to factor, like I did in grade school, the pi out. And now, this is going to tell me that pi is either 1 or minus 1. Why is that true? Well, I've got two integers. They're not fractions. So the only way that two integers, if I force them to be non-negative, that means also that it's got to be only 1. But if I allow them to be negative numbers as well, then the only way two integers could multiply up to be 1 is if they're either both 1 or both minus 1. That's because no fractions are allowed, so they can't be anything but 1 or minus 1. But now we have a problem, because by definition, no matter how you defined it, as prime numbers can be negative and positive numbers that are only divisible by 1 and plus or minus 1 in itself, or if you use the first hit off of Google, which says that a prime number is a whole number greater than 1, whose only two whole number factors are 1 in itself. Either way, I'm in trouble, because right now I have that prime number must be 1 or minus 1. That's a contradiction, because prime numbers can't be 1 or minus 1. And so where I started out with my assumption that there's a finite number of primes must be wrong, because I ended up in a conundrum. So the opposite must be true, and there are an infinite number of primes. You would think that I wrote too much. That's what usually students think. This is actually a pretty minimalist proof. And so it gives you an idea. And I would look up other proofs online of this same theorem. People have different styles in how they write. I'm a bit more flamboyant. You'll see people who are more sticklers and use formal language. I don't. So everybody's got their style, but there's certain ingredients that are in all proofs. And so I would recommend actually looking at them to get an idea of what ingredients have to be there to constitute a proof.